Greetings, students. So here we're going to look at a phase change diagram. So what this diagram has is we have our solid, liquid, and gas. So remember, solid, the particles have really strong attraction, so they stay together. Liquids, they have some attraction, so they're starting to come apart. And gases, there's minimal attraction, so the particles are moving all over the place. How do you do that? Well, you add heat energy to the substances to make them turn from solid, liquid to gas in this direction. Or if you were coming the other way and moving to the left here, you would then remove heat energy. And then we'll talk about what's happening with temperature. But I like to think about it when I'm heated. If someone were to put a fire underneath my hand, am I going to keep my hand there? No. I'm going to try and move that away if possible. So that's typically what you're going to see is going to happen. So let's take a look at this and see what happens. So here, I'm going to zoom in on this a little bit. I go from solid to a liquid, so this change in state is solid to liquid. And you guys should know that if I go from solid to liquid, that is called melting. Now there's some really interesting things going on when you see this. So here I'm heating something the entire time, but what do you notice over here about the temperature? The temperature stays constant. Okay? And so let's take a look at this. So I want to start with solid and end with a liquid. And so let's see what happens. So you're heating it, heating it, heating it. And then during melting, as you see, during melting, the temperature is just staying the same. How can that be? You're heating the entire time. How can that not go up? Because you have like a fire under something. Typically, people will think if I have a fire under something, it is then going to, the temperature is always going to go up. And that's not the case. Right? So we have to see what's going to happen with that. I'm going to pause this and type in here, and boom, there it is. Temperature remains constant during a change of state because that heat energy is used to overcome the attractive forces. And you'll be able to see this in the lab. We'll prove to you that this works. Okay? So let's take a look at again why that's the case. So again, I start heating it up, not seeing a lot. They may vibrate a little bit more, but during the melting, do you see how these molecules, these particles are able to move more? So that took it. Those magnets were close together, and they want to stay close together. So if I have to pull magnets apart, that takes energy. And so that's what's happening is that those particles want to hold together. I use the heat energy from the stove to pull them apart, and then they can start moving faster. And when things move faster, that's temperature, kinetic energy. So first, use the energy to pull them apart, no temperature change. Then, once they're moved apart, then they can start moving, and that temperature change can go back up. So let's keep going back to this one. So this next phase change is going from liquid to gas. This can be called a lot of things. The most common one is vaporization or vaporizing. It could also be referred to as boiling or evaporating. Evaporating typically only happens on the surface, where vaporization or vaporizing and boiling, those happening for everything. But those are all going from liquid to gas. Okay? And again, you'll see the same piece here. Right? That during that phase change, when you're boiling, it's going to do the same, and temperature is going to stay constant. So let's go from liquid to gas. We can kind of see what's happening here. Right? They're moving faster and faster, but those bonds are still holding them together. They can't just leave. But once you hit that boiling, again, you're taking those magnets and you're pulling them farther apart, and then they can move after that. So again, you're seeing that that temperature won't change. You won't be able to get over 100 degrees Celsius, or if we're doing it with Fahrenheit that you may have more common, you will not get, under standard conditions, water above 212 degrees Fahrenheit. So that's pretty cool. Everything we tell you, we want to be able to prove it, and that's what our labs are for. Let's go back the other way. What about gas going to liquid? Gas going to liquid is condensation. Okay. It's a little trickier going back the other way. Essentially what happens if you think disorganization going to organization. Whenever you do that, you have to expel energy. Right? So you have an even distribution of losing energy going one way and then using that energy going back the other way. So that's why those ones have that constant temperature as well. Anytime you have a phase change, you have a constant temperature. Let's see, liquid back to solid. Hopefully you're very familiar with that one. That is called freezing. Some other interesting ones you may never have heard about before. Down here, solid directly to gas is sublimation. So it just skips over the liquid phase. And dry ice is one of those that we have. Why do they call it dry? It skips the liquid. So it just jumps from solid directly to gas. The other one going the opposite way is from gas all the way to a solid, and this one is called deposition. So you'll have to know all of those, so make sure you have them down. So we have lots of different things going on here. Then the last thing we want to show is, we saw it in the notes earlier, but it's all about having physical changes. Because if we look at these, am I getting anything new? Okay. I'm heating it up. Those molecules are vibrating faster, so that's why they have that. Now I'm pulling apart those attractive forces, using that energy. Temperature's not going up. Now those attractive forces are broken, so now they can get moving and moving and moving, and that's why you'll see temperature goes up. Again, if you look at these little particles, am I getting any new particles? Am I getting a new substance? No. So you have to look at it from a molecular level, that inside those molecules, you're not getting anything new. Even though it looks new on the outside, it is not actually new. Also, you can reverse it, just taking that energy away.